Okay, today's lesson, take some mashes up, you guys do the mashups of a bunch of geometric concepts we've already discussed into something brand new. So we're going to review most of the vocabulary that's up here to get to our theorem we're studying today. So we have a right triangle. A right triangle has a right angle, exactly one right angle. The side across from that right angle is the hypotenuse. The other two sides are the legs. The legs are perpendicular, creating the right angle. And now we have another aspect of a triangle. A triangle will have an altitude. An altitude is a segment that goes from a vertex perpendicular to the side opposite. So if you notice, an altitude can reside inside the triangle or outside of the triangle. The altitude of each of these triangles is this dashed line, and the altitude of a right triangle would be either leg. However, there are three altitudes in each triangle because there's three vertices and three opposite sides. The one that we're interested in is the altitude that goes from the right angle perpendicular to the hypotenuse. So let's get our bearings and just label these right triangles. What I do first is I find the right angle and then I put in the hypotenuse. And the other two are just the legs. And once I find the hypotenuse, the hard part is finished. Again, find the right angle, go across, write the hypotenuse. Write the entire word. Do not just write H or HYPT or whatever. Spell it correctly. Practice it now so that you get it correct on the test. Find the right angle, go across from it, label that side the hypotenuse. The other two are legs. Ignore all the superfluous, that means extra information. Find the right angle, go to the side across from it. That is the hypotenuse. And the other two sides are the legs. Right, now you're going to use the straight edge on the protractor to draw in the altitude that we will be studying today. We already have two of the three in these right triangles. We want the third one that goes from the right angle perpendicular to the hypotenuse. From the right angle perpendicular to the hypotenuse. Okay, now we need to do some measuring. So we want to explore exactly what type of triangles are formed. We have two right triangles, but we're interested to see if these two right triangles are similar to each other. We don't want to have to do more work than is necessary, so let's review the three ways that we can show triangles are similar. We can use the angle similarity theorem, the side angle similarity theorem, or the side similarity theorem. So what we've done is we've constructed that altitude, and now we've separated the two triangles, and we're going to do some measurements. I'm going to measure everything just in case, I don't know what you're measuring. So I'll measure all of them and come to my conclusion. Okay, what I'm not going to measure is angle P, because angle P is a right angle, and I know that has to measure 90. I'll measure the other two angles in the triangle. Doing them all. Measuring all my angles at once. Remember, you might have to extend the sides here that form the angle to measure the angles, especially in the smaller triangle. I'm going to measure the sides. I'll measure the sides of the smaller triangle. Then I might just want to do a quick check of my measurements. I check my angle measures by making sure that their sum is exactly 180, and I check my lengths of my triangle sides. It's kind of a quick check. As long as the hypotenuse is the longest side, I'm feeling fairly confident that I have good measures. And I would check with other people in my group to make sure that we're getting similar measurements. And my conclusion, regardless of which theorem I use, angle, angle, or side, angle, side, or side, 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 my conclusion is the same. The two triangles are similar, and to write the similarity statement, I have to match up the corresponding parts. So angle C corresponds with angle W, P corresponds with P, and W corresponds with H. So that's a pretty neat fact, and it is a theorem. We are going to be studying two theorems that have to do with right triangle and altitudes and creating similar triangles. The overriding theorem says that if an altitude is drawn from the right angle to the hypotenuse, then the two triangles that are formed are similar to the big triangle, we'll study that tomorrow, and similar to each other, which is the one we're studying today, the altitude hypotenuse. Again, it says the measure of this altitude, that's the segment that goes from the angle to the side opposite, specifically the right angle to the hypotenuse, is the geometric mean. Okay, if we go back to the definition of the geometric mean, it has to appear both in the numerator and denominator of ratios that create a proportion. And the other two parts of that proportion are the segments that are created by drawing in that segment, that altitude. So one way that you can remember this theorem is segment altitude equals altitude segment. Another way is I like to circle the altitude because that's what I know repeats. What is the geometric mean? And then I make a little rainbow. And I follow the rainbow, writing my proportion. Segment altitude equals altitude segment. We need to remember that we need the equal sign in between our two ratios, otherwise we do not have a proportion. All right, so let's do these 4 examples here. What I want to do first is find that altitude and circle that. And then I draw my rainbow, and then finally I write my proportion. 4 is to x as x is to 9. Solve for x. So I have x squared is 36. Here x is 6. And you might be saying, oh, wait a minute, Miss Fasola. You made a big stinking deal last semester that the square root of x squared is the absolute value of x, which is so completely still true and valid. However, the definition of the geometric mean is that it is of 2 positive numbers and it itself is positive. And here, if we think about putting down a -6 for a segment length, that does not make sense. So here, the answer, because we are in an application, a geometric setting, is only the +6. So I go to the next picture. I find the altitude. That's what I circle. Okay. Do not make the rule that the variable is always the thing that's the geometric mean. That is not true, because I see that's not true in this example. The geometric mean is always whatever is written next to the altitude. Sometimes it's a variable, sometimes it's a value. I have x is to 8 as 8 is to 4. And I solve for x and I get x equals 16. Find the altitude. This is the geometric mean. I'm drawing my rainbow. I'm starting to get ready to fill in my proportion, and I say, well, wait a minute. I'm missing one of my measures, but it's easily found because I'm given the entire hypotenuse and one of the segment lengths. So I just do some subtraction to get the segment measure I need. And now I write my proportion. 36 is to x as x is to 64. Solve for x. X is 48. Last one, I find the altitude. I draw my rainbow. I set up my proportion. Segment is to altitude as altitude is to segment. Solve for x. And here, x equals 9. Now at this point, you know enough to be able to calculate the length of the bridge across the canyon, which you drew in the diagram for at the beginning of class today.